Hi viewer, this is EasyElimu channel. I'm Vincent Kanamwai and I'll be taking you through Form 2 Mathematics, Indices and Logarithm. Stay tuned as I welcome you all. I shall start with the indices, and under indices we shall consider certain numbers, such as I'll consider number 25, which is the short form of writing 2 multiplied by 2 up to 5 times. This is short formed to this. Now here, as you can see, this 2 is referred to as the base. And 5 here is the index or the power. Now let's just refer to it first as the power to which the base 2 is raised to. Now this 5 here we have said is the power to which 2 is raised, to mean that this 2 has to be multiplied itself up to 5 times. Now 5 here, or the number to which the base is raised, is referred to as index, which is in plural referring to as indices. Now we shall consider in general form, in case we have a raised to n. This simply means that a is the base, but we have to multiply a up to n times, whereby n here is a positive integer, or maybe a negative, but it is an integer, a number. So a is raised up to n times, meaning that a is the base and n is the index to which the base has to be raised upon. Now we shall see some of the examples. For example, we may see like a cubed, having a number like a cubed. This simply means that we have to multiply a 3 times. So meaning that a cubed is the short form of writing a multiplied by a multiplied by a. And if we have another number like 4 raised to 4, this 4 here is the index to which the base 4 is raised. I'm referring to the base 4, and 4 there being the index or the power. Now this simply means we have to multiply 4 up to 4 times. And if you have that one, you will have to get the value as the first one will give you 16. 64 multiplied by 4, you will get 256. So meaning that 4 raised to 4 is giving you an answer of 256. So writing this one can be short formed or short written into 4 raised to 4. Now this is what we are referring to as indices. So meaning that index is the power to which any number is raised upon. Next, we are going to see the laws of indices. Let's now handle laws of indices. Under laws of indices, we shall consider several kinds of numbers. For example, let's consider the following. We have a5 multiplied by a squared, a raised to 5 by a squared. Here, you will identify that you have to multiply, the first one will be a multiplied by a 5 times. Then you continue multiplying a twice. So we shall continue twice. This one here represents the last a squared. And this a raised to 5 is the short form of writing a up to this point. This one here is what we have short formed to a raised to 5. And this one is what has been short formed to a squared. Having that, as we had said earlier, a here is the base and 5 is the index to which a is written. Now, if you do this, you will end up having, this one will give you a base. Since the base is the same, it does just means that we are going to multiply all of this and we shall get a raised to 7, because you will have 7 of them, 7 times of a's. So it will be a raised to 7. In otherwise, this one can be short formed or short written as, instead of writing a long method or a long way, you can still write a 5 raised to 5, then you add the powers, and you will find the same answer, in that this one will give you a raised to 7. This one here will give us the first law of indices. It will give us the first law of indices, and that law is called a sum of two powers. Because we have dealt with the two powers of indices, so it will be the sum of two. It's referred to as the sum of two powers. Now, instead of just going the long method, you can just do the short form of it, whereby you will add the powers since the base are the same, and you get the value there. Let's consider another one with the division, so that we may have a raised to, for example, let's say 5, divided by a raised to 2. This is the quotient rule, so we shall apply the quotient rule here, and we shall have a is the same as writing a raised to 5 divided by a squared. And here, if we write it in long method, we shall find that this one is the same as writing a multiply a 5 times divided by a multiplied by a. If you have that, since the items there are identical, we can simplify it by simplifying two of them on the numerator, which cancels the denominator by getting 1 here, and you will find the remaining will be a multiplied by a multiplied by a, and you will have a cubed. Meaning that if you have a raised to 5 divided by a squared, on simplification you will get a cubed. In otherwise, you can still work out in a short form of this, whereby we have a raised to 5 divided by a squared, and this one you can work out by taking, since the base is the same, it only works if the base is the same. Since the base here is the same, you can take a raised to 5 minus 2. That one here will still give you the same answer as a cubed, and this one here is called the difference of two powers. That one there is the difference of two powers, whereby we have dealt with the first power of 5 and that of square. But sometimes you may have numerous of the powers, but with the same bases. You will still do the same, but the difference of the powers will depend on how many items are you dealing with. For example, maybe this one could be included with another division here and could be divided by 2a raised to 2. The same could be applied, whereby now here you could include minus 2 so as to have a raised to 1. In case of that, we shall say that is a difference of 3 powers. But for our case, this one was an exclude, and we got a raised to 3. We shall consider another one, whereby we have a raised to 5, but this one is still in a bracket or is bracketed and then 2 placed outside. In that case, this just means you have to take a multiplied by a multiplied by a 5 times. Then whatever you have here, that is the first which is in bracket, but it is being squared. If you write in long method, the first one being squared means you have to take the same value here, you multiply itself twice. So if this one is 5 times, you continue multiplying by the same base, in that you will have This one is a raised to 5, the same to the one which we have otherwise. What is in the first bracket is a raised to 5, and what is in the second bracket is a raised to 5. So if you do the same, you will find that if you multiply this and you open the bracket and multiply again with the second bracket, you will end up having a raised to 10. You will end up with a raised to 10. So meaning that we can just simply take, if you have a raised to 5 squared, you can just take a, since the a is the same base, then this 5 here, we just multiply the powers if it is in bracket and the adjacent bracket is being squared. No matter what power will be outside or inside, what you just do, you multiply the powers and you will get this one is a raised to 10. The same value which we have obtained here, the same answer if you work it in a long method as we have seen. This one here is known as the product of two squares. That is known as the product of two squares. With that, we can give a general form of it, whereby we shall say, in case we have a raised to m, let's take a b raised to power m, b multiplied by a raised to n, then this one, according to the first law of index, which we have observed, and that is the sum of two powers, we shall have a raised to m plus n. That is what we obtained when we worked the first example using a as the base and the power 5 and 2. We found that. This is the first law of indices, and we have said this is the law of the sum of two powers. Then another law we observed when we did with a division or quotient, and we said in case we have a raised to m being divided by a to power n, we shall find is the same as taking a raised to m over a n, but this one can be simply be worked out by a raised to m minus n, and this is the value for what you will find after working it out. Then the third law we have observed, which is now the product of two powers, and we have found that this one can be given by if you have a raised to m and outside of the bracket we have n, you can still find the value of that by taking a, but now the powers has to be multiplied. So you will have m multiplied by n. So this is the value which you will find if you multiply it. And this one is the third law of indices. Next, we are going to see some of the examples if we work it out with the same basis. Let's take the first example containing the first rule or pertaining the first rule of index or the law of indices. So we shall consider an example whereby we have 5 raised to 7 b multiplied by 5 cubed. And according to the first law of index, we shall find out that this one is the same as taking 5. Since 5 is the same base to the two items there, we shall take 5. Then to the powers, we shall add, because it's the first law, so we shall add the powers, and you will find it is giving you 5 raised to 10. And if you do the long way of it, or the long form, you will find you will still arrive at the same answer. In case you have 6 raised to 9 being divided by 6 raised to, let's say, 4, you will find out this one lies under the quotient rule, and that is the difference of two powers. And if you work it out, you will find since you have the same base, you will end up having 9 minus 4, as per the rule, the second rule of index says. So you will end up with 6 raised to 5, and that is the value of that calculation. And if you work a long way of it, you will still arrive the same value. Let's see the third example, and this one pertains the product of two sums, the product of two powers. And this one is, for example, if you have 3 squared but being raised to 4, you will find, we say this one, since we have the same base, we shall just take 3, but the powers we shall multiply, and we shall find this one is going to give us 3 raised to 8. And that is some of the examples you will find or encounter during when you work out some of the problems pertaining laws of indices. Next, we are going to see how we can evaluate the zero index, or what do we mean by zero index. Now, let's consider the zero index, and we shall consider an expression such as a raised to m being divided by a raised to m, whereby they have the same base, but we are dividing. According to the second law of indices, we say this one can simply be worked out by taking a raised to m minus m. Or you can still do it the long way by taking a raised to m, then you divide by a raised to m. And you will find that here you are going to divide, and you will find here a raised to m into a raised to m, you will find is 1. And the same applies to here. So you will end up with the answer as 1. But if you do it using the second law of indices, you will have this one as a raised to m minus m, you will get is 0. So it will be 0. So this simply implies that in case you have a number being raised to m or to a given power, then you divide the same number or the same base being raised to the same power, you will end up having that number being raised to 0. And any number, be it 1,000 or 1,000,000, being raised to 0, it will give you 1. So we can say that if you have a number a raised to 0, you will find that the value or the result will be equal to 1. That implies that no matter how big the number is, for example, if we have that, you raise it to 0, you will still pertain the same value as 1. Or if you have, for example, let's take 5 raised to 4, then you divide by 5 raised to 4, you will end up having 5 raised to 4 over 5 raised to 4, and this one will give you 1. Or if you do it using the law of indices, you will find this one will give you 5 raised to 4 minus 4, and you will get this one is 5 raised to 0. And we have said any number being raised to 0 will give you 1. So that is what we are referring to zero index. So here, this 0 here being raised to is what we are referring to zero index. And we have seen that if you raise any given number to 0, you will get 1. So next we are going to view some of the examples on what we have learned there and how we can find some of them down. Let's consider an example such as you are being told to solve 2 into x equals to 12. And another thing you should pertain in your calculation before you do any exercise on indices is make sure that whatever you work with is of the same identity or base. So if you want to work any number with the same index or to a given index, make sure if it includes the product rule sum or that difference rule, then you have to make sure that the base is the same. For instance, for this our case here, it simply means that if we take 2, then we use this product rule, should be equal to 2 raised to 12. So meaning that our 2 will be x multiplied by 3, and we shall get 3x should be equal to 2 raised to 12. And if you do that, it simply means that since the bases are the same, then the powers also are the same. So we can take the powers alone so as we can find the value of x. And to find the value of x, you have to divide both sides by 3, and you will find your x is equal to 4. So meaning the missing value there in the above expression is 4. So if you replace here 4, you will find that the two sides are equal. Next, I will give you one to work on it, whereby you have, this one is an exercise for you. We have 2x raised to 4 is equal to 81. And hint is that make sure, if you're dealing with the indices, make sure the bases are the same. So if that is the case, I believe you can work out that one by using the same procedure as we have done there. Next, let's see how we can find negative indices, or what do we mean by negative indices. And we shall consider a given expression such that we have a raised to negative n, which is a negative index, being multiplied by a raised to n. According to the first law of indices, we shall find out that if we use that, we are going to have a raised to negative n, but since we have said it's the first law, and first law is the sum of two powers, then we are going to add the power since the bases are the same. And if we do that, we are going to have a raised to 0. So that implies that a raised to negative n multiplied by a raised to n is equal to a raised to 0. And if that is the case, we can say that if you have a raised to negative n, is the same as writing a raised to 0 over a raised to n. That means we are going to eliminate a raised to n on this side by dividing both parts by a raised to n. In that, if we do that way, we will have this kind. That this side we are dividing by a raised to n, a raised to n, so that we may remain with a raised to negative n. And if that is the case, we are going to have a raised to negative n is equal to a raised to 0 over a raised to n. But remember one thing. Remember, we said that a raised to 0 is equal to 1. That was the 0 index. That if you have any number being raised to 0, you will get 1. And in this case here, we have a raised to 0 over a raised to n. So meaning that in case you have a raised to negative n will be equal to 1, because we are going to replace where we have a raised to 0 by 1 and being divided by a raised to n. So that means that in case you have a number or a negative index, then it's the same as writing 1 over that number without the negative index. So the negative index changes to positive index as we have seen there. Let's view an example. For example, we have 2 cubed divided by 2 raised to 4. If we have a certain number like that, then it means if we use the second law of indices, then we shall have 2 into 3 minus 4 since we have the same base, then we have to subtract the powers, and we shall end up with 2 raised to 1. And since that is what we have, remember this 3 here is less than 4, so it shall be 2 raised to negative 1. If that is the case, remember what we have said. Since we have 2 raised to negative 1, we have said, according to this law here, is the same as saying 2 raised to negative 1 is equal to 1 over, now an will be the number here, a raised to negative n, without the negative sign. So meaning there, a raised to negative n is being represented by our number here, 2 raised to negative 1. Now we shall rewrite it with 2 raised to 1. And this one is the same as writing 1 over 2, which is a half. So that is how we do rewrite it. That is the negative index. In case we have another example such as 2 over 3 raised to negative 2. In case of that, then considering the same law of negative indices, we shall find out that this one here is the same as writing 1 over this number here, 2, this 2 over 3 is the same as a, which is negative 2, is the same as writing 2 over 3 is the same as a raised to negative n, whereby negative 2 is what we have here, negative n. And 2 over 3 is our a. So having that, we can still rewrite that one in that form, and we shall have 1 over 2 over 3, but now the power will be positive. So that is what we shall have. And if we have that, we shall say it is 1 over, now this one will be 4 over 9. But if you take 1 divided by 4 over 9, we are going to have 9 over 4. You will end up with 9 over 4. If we work out, you will get that's what you will have, 9 over 4. And that one is going to give you 3 over 2 if you simplify squared. It's just getting back to what you have. So meaning that in case you have a fraction being raised to a negative index, for example here I have 2 over 3 raised to negative 2, the value which I will get is just the same as interchanging the fraction, which it will be, for this case will be, if I interchange, I will have 3 over 2 squared. And if I have 5 over 6 raised to negative 3, then I will just interchange here 6 over 5, then the power shall remain positive 3. That is the value which I will find. We have found that by working it out, and we have seen how it works out in case it is a fraction. But if it is not a fraction, then the laws should be followed correctly as we have been working it out. For your case, now work out and see if you can find out, in case you have been given 6 raised to negative 4 being divided by 6 raised to negative 3. No, let's just take positive 3. Work out the value of that and see what you will find, bearing in mind the negative indices. Work out that. Next we are going to see another one, and that's the fractional index. We see how we can evaluate, or what do we mean by fractional index. We shall find that fractional index most of the time are written in the form of P over Q. And in this case here, you will find out that P and Q are integers. And these integers are in such a way that Q is not equal to 0. Q is not equal to 0. And they don't have any other common factor apart from having a common factor 1. So meaning that P and Q, their only common factor is 1. That is how you will find fractional index being written in form. So meaning that in case we have a squared being equal to b, then this one here, it simply means that a here is equal to square root of b. How is this possible related to fractional index? We have said fractional index is written in the form of p over q. But here I have written square root of b being equal to a, whereby a squared is equal to b. It simply means that this one here can be rewritten further by saying that a here can be obtained by taking a, but now this square root here is the same as writing 1 over 2. 2 here implies that this I have implies that we have to find the square root of, it is b I have. So implies that in case you want a, you have to find the square root of b. You can either rewrite the square root of b in this form or write it in the other form. So meaning that we have a equals to b I have, which is simply writing the square root of b. So this I have here is what I'm referring to as fractional index. The same applies in case we have a cubed. You will have, if a cubed is equal to b, then it simply implies that in case you want the value of a, you have to find the cube root of b. And finding the cube root of b is just the same as finding the cube root, but written in fractional form, the fractional index form, you will find that it is b raised to a third. And if you have a raised to 4, b equal to b, then it implies that a here is equal to the fourth root is written in that form of b. And this one in fractional index can be rewritten by 4 raised to a quarter. So if you find a number being written in that form, know that that one there, we are finding the fractional index of the given number in order to find a given integer or number. So we shall consider an example on that, such that we have 16 raised to a half, but it's being squared. Let's just consider an example, 16 raised to a half being squared. And this one here, we can see that the one in bracket here, it is under the fractional form. And we can see that if you rewrite it in a long way, you will find that you are going to have 16 raised to a half multiplied by 16 raised to a half. Since it is square, it means we are going to rewrite the same number in the bracket itself twice, and we shall have that value there. And according to the first law of indices, you will find that this one is the same as writing 16 raised to a half, but since we have the same base, it will be a half plus a half. And this one here is going to give you 16 raised to 1, which is the same as 16. Following the fractional index law, you will just find out that 16 raised to a half, which I have said simply is the square root. So you will have the square root of 16 and you will have to raise it to 2. Rewriting this one in this form, so 16 raised to a half can be written as the square root of 16 and then the square being outside. And if that is the case, you will find that the square root of 16 you will find is equal to 4. But remember, this is what we have in bracket. And outside the bracket we have raised to power 2. And 4 being squared, or 4 multiply itself twice, you will find your answer being 16. So meaning that 16 raised to a half squared, you will find the answer is 16. Whether you work it with the other way or you work it directly as using the fractional index, you will still get the same value. So in general, that simply means that in case we have a raised to 1 over n, it simply means that this one here will be equal to, since a is the base here and 1 over n is the fractional index, then we can still write that one in a form of whereby a will be in the square root sign, and here what we have here as the fractional index, and here will be the root to which a must be found. So here we shall have the root n. So we shall have n root of a. And then we can extend by saying that in case we have another one whereby we have a being raised to m over n, we shall write this one as, since this one is a fractional index, we shall still write this one in form of a root sign, whereby a will be inside the root sign, and n here will be the integer or the number to which the number under the root sign must be found. So we shall find it to that one, but after finding it, we have to raise it to the numerator of the fraction. So will be 2 power m. With an example, we shall view 25. Let's find 25 3 over 2. So 25 raised to 3 over 2 is the same as rewriting that number in the form of 25, the root sign 25, and here we place 2, which can be just be simply the square root sign, and all of it we shall find the cube of that value. So meaning that we are going to find 25, but the square root of it, 2 means we are having the square root of 25, and 3, after finding the value, you have to find cube root of that value as according to this law. So we shall end up having the square root of 25 is 5, but we shall cube, so you will end up having 125 as the value of what we have there. And that is simply what it means by having a raised to m over n as a fractional index being written in this form, and on real calculation you will find it lies under the same calculation as we have done. With that, I believe that you will have to work any form of sum or computation or problem you may encounter dealing with indices as we have worked out. Now let's see or learn about logarithms, and we shall consider given numbers under logarithm. For example, we are going to have 4 raised to 0, and remember from our indices we save a 0 index such that 4 raised to 0 will give us 1. And if we have any number raised to 1, is the number itself. But if you square 4, you will get this one as 16. And if you cube 4, you will get 64. And if you take this 4 raised to 4, you will have to get 256. Here, you can continue with the list endless, such that you may even add 4 raised to 5, 4 raised to 6 until onwards. But what we are interested in today is logarithms, and we shall find, we said that here 0, 1, 2, 3, 4 up to the end, we said is referred to as the index or indices. For them are numerous here, so shall be indices. Now, logarithm here just means the indices 0, 1, we have indices 0, 1, 2, 3, 4, up to the endless, are the logarithms of the corresponding numbers, and the numbers I'm referring to are 1, 4, 16, 64, 256, endless, to the basis of 4. So meaning that 0, 1, 2, 3, 4 are the logarithms, but for this case you can view them as indices. But these indices now here represents our logarithms of the corresponding numbers to the basis of 4. So meaning that in case we take this one here, we can say this one here 16, here 16 is the logarithm. We can say 16 is the number to which 4 must be raised to find 2. This is in index notation. So meaning that we have logarithm of 16 to the base of 4, we shall find is 2. So logarithm 2 is of the number 16 to the base of 4. And logarithm of, let's say, 64, but let's say 256. Logarithm, we can write in full, but I'll write in for short form. So logarithm of 256 to the base of 4 is 4. As we can see, here we have 256. So the logarithm of this 256 to the base of 4, we shall find is 4. So meaning that the logarithm of 256 to this base, you will find that one. We can short form or short write that one in a form of log. Now this of 16 will be 16, but we are dealing with the base of 4, so it shall be the base of 4. We shall find the answer is equal to 2. And here we have the logarithm of 256. The same is to the base of 4, and that one will give us the value as 4. Remember, here is what we had. What we have written here, we refer to it as index notation. But if you write it in this form here, is what we refer to as logarithmic. Is referred to as logarithmic notation. So if you have numbers written in this form, or your computation or equation being written in this form, then you are writing it in logarithmic notation. But if it is in this form, it is index notation. And the way of changing a number written in index notation to logarithmic notation is just simple. In case we want to rewrite this one in logarithmic notation, you just say the logarithm of 1 to the base of 4 is equal to the power. So meaning that it will be the logarithm of the number to the base of which the number is to be raised, and then it will be equal to the power or the index as we have done here. So it's just simple. In case you want to rewrite this one to index notation, you just say it is the base here, which is 4 to start. Then after that, you will have to raise it to that number to which you will find that logarithm. So it is 4. Then after finding that one, then your value will be equal to 256. That is how we rewrite it back to index notation. Let's see some of the examples. Let's check. For example, 3 raised to 4 equals to 81, and you are being informed or asked to write that one into logarithmic notation. If you want to write that one into logarithmic notation, remember what I told you, you start with this. So you will say logarithm of 81 to the base of 3. So 3 will be written down there, will be equal to the power to which that base is raised. So the power is 4. So shall be to the power of 4. And in case you have been issued with a number like logarithm of 125 to the base of 5 equals to 3, and you are being asked to find or to rewrite that number into index notation, what you do here is you write 5 down here. This is in logarithmic notation. And the other one which I want to write here, this one here is index notation. So So we need to rewrite the one we have here in index notation. And rewriting it in index notation, you start with the base here, which is 5. Then you raise it to the number which you have found as the logarithm of what you have. So it will be raised to 3, will be equal to the value here. So you come back to this. So it will be equal to 125. That is how we compute or rewrite a number being in index form or index notation to logarithmic notation and vice versa. That is how we do. In case you have that one I've shown you and this one I've shown you. Now let's consider the following numbers. For example, I have 15. I have number like 150. I have another one like 1,500, 1,500,000, and so on. And also I have a number like 0.0015. I have 0.0000157, and I want to rewrite this number into standard form. You will find out that for the first one, this one here is the same as I rewrite it in a form of 1.5 multiplied by 10. Since the decimal point, I have moved it to this point in order to rewrite it into standard form. Then my power will be positive. So I will have to power 1. And that is the index form of that. The standard form of that, but the 10 here I've written it in index form, as you can see. So meaning that if I take 1.5 times 10 raised to power 1, I will still get the same value as initial, which was 15. The same apply to the second one, and here I will find is 1.5 times 10, but here the decimal point will move from the extreme end of the right hand side to the left 2 places, so it shall be raised to power 2 because I'm moving this way to this point. So it shall be that point, and we shall have 1.5 times 10 raised to power 2. And for this case here, as you can see, you can help me, is 1.5 times 10 raised to power, yeah, good, it's power 3. So you will find is to power 3. And the other one here, what do you think should I raise it to? And you will find is 1.5 times 10. To what power should I raise? Yeah, good. You will find is to power 6. Because the decimal point will move from the extreme end of the right hand side to the left 6 places. So it shall move from here to here, and that is 6 places. I shall raise it to 6. And now this one here, since the decimal point is here, we can move it to a number where we have a number or a whole number. So on moving, we are going to move the decimal point to the right, and moving it to the right, we shall count the number of places we are moving. For this case here, we shall have 1.5 times 10. But since the decimal point has moved to the right, our value here, 10, we shall raise it to a negative index, such that it shall be to the negative number of places we have moved, and that is to negative 3. And for this case here, we are going to have it be moved to 1.57 times. Now you can view it yourself and guess to what index you lie, right? 10? Yeah, it's negative 7. That is what we have there, because the decimal point will move to the right 7 places, and we shall have 1.57 times 10 raised to negative 7. So that is what we have there. What I have written here is what we refer to standard form of the respective numbers. As you can see, this 15 has been written as 1.5 times 10 raised to power 1. This is the standard form of writing 15. So in general, that means that if you have a number and you want to write it in a standard form, it will be rewritten in a form of a times 10 raised to power n, whereby a is a number between, a here is a number between 1 or 1 itself. It may be a 1 or a number beyond 1, so we say is a number which is 1 or more than 1, but that number is less than 10. So that means it can be 1 up to 9, but it's less than 10. And n here is an integer. N is an integer, so meaning n is a number to which that number should be raised. So that is how we can write a number in a standard form. So I shall give you an example. I have computed here one, so I want you to work out, in case you are being given 0.46 over 10,000. Write that number into standard form. What do you find? Next we are going to see how we can find or see powers of 10 and common logarithms. Let's now see the powers of 10 and common logarithms, and here we are going to consider different kinds of numbers of 10, of tens or multiples of 10. For example, we shall consider the numbers such as 1, 10 itself. We shall also consider 100, 1000, and so on. And if we write these numbers in index form, we shall find out that the first one here, in order to get 1, we shall write it as 10 raised to 1. 10 raised to 0 will give us 1. And if you want to get 10, it shall be 10 raised to power 1. You will get 10. The same applies to 100. So if it is 100, it shall be 10 raised to power 2. You will get 100. If it is power 3, you will get 1,000. And if it is power 4, it's 10,000. And if it is power 5, is equal to 100,000. And this process continues onwards. That's how it continues. And we shall find out that in this case, here we have 0, 1, 2, 3, 4, 5. This 0, 1, 2, 3, 4, 5, we said they are the indices or powers to which 10 are being raised to find the respective or corresponding numbers, which are 10, 1, or 100, as we can view out. Remember we said this, that 0, 1, 2, 3, 0, 1, 2, 3, 4, we have even 5, and so on. If we could have continued, these are the logarithms. They are the logarithms of 1, 10, 100, 1,000, and so on to the basis of 10. They are the logarithms of number 1, 10, 100, 1,000 respectively, so on to the basis of 10. But sometimes we can find that we have some numbers which don't lie between which lies in 1, 10, 100, 1,000, and so on. It lies between the two numbers. It may lie between 1 and 10. It may lie between 10 and 100. So it means determining the logarithms of that number, or the powers to which 10 must be raised to find the numbers, is a little bit a challenge. So in that case, we need a way in which can help us to identify the logarithms of the respective numbers to the base of 10. With that, that is why we use the 4-figure elementary mathematical table, which will help us to evaluate the logarithms of the given numbers. For instance, we shall consider a number such as 70. In case we have 70, We know 70 here lies between 10 and 100. In between 10 and 100 we have 70. But we know the logarithm of 10 is 1 to the base of 10. The logarithm of 100 to the base of 10 is 2. So meaning that this one here is the same as writing 10 raised to 1 and this one is 10 squared. So you will get 100. So meaning the logarithm of 10 is 1 and logarithm of 100 is 2. So meaning the logarithm of 70 lies in between 1 and 2. So we need to compute that value in which we can find the real value or the real logarithm of 70. And in order to find that, that's the reason why we incorporate what we have already learned, what we refer to as standard form. And in that case, we shall rewrite 70 in standard form, and it shall be 7.0 times 10 raised to power 1. In this case, if we have this, we shall now say, since we have 10 raised to power 1, this power here is the log to which we shall find that. So we are going to find the log of this, and if we find the logarithm of, we are going to find the logarithm of 7.0 times 10 raised to power 1, and if that is the case, we shall end up having 1. Now point, this 1 arises from the logarithm of 10 raised to 1 is 1, because it is to power 1. Now we need to find the logarithm to which, with the base of 10, 7 must be raised, 7.0 must be raised in order to find this number. So we shall find out using the mathematical table. And in order to find that, we shall view out using the 4-figure elementary mathematical table. You go to the logarithms of numbers base 10. You will find it is written, we have logarithm of numbers to base 10, and it's written in bracket log 10x, that way. And then we have a table there. Under this table, we have at extreme left hand side, we have x on top. And then in between there, we have 0 to 9. And then on the other side, you will start by having add. There is add on the other side, a column of add, first a row of add, and then below the row of add, we have 1 to 9. 1, 2, up to 9. That's how it has been written. So, if you want to find the logarithm of 70, first you write it in standard form, and we have found the first one we will have 1. Then, since 7 is between 0 and 10, is between 1 and 10, then it means what we shall find is less than 0 to 1. Since we need to find the logarithm of 7, and we know 7 is a number between 1 and 10, meaning its logarithm should be between 0 and 1. So we need that value, and to get that value we need to use or have an help from the logarithm table. So that is what we are going to see, and then we are going to find the logarithm of 7 to base 10 using the mathematical table. And there we are going to view 7.0. So here you have some of the, you have a table here of the logarithm, and on top of it, heading is logarithm of numbers base 10, as you can view here. And in bracket we have logarithm to base 10 of x, where x represents the number to which you have to find the logarithm. But here we have to find the logarithm of 7.0. And on this page, as you can view under the column of x, you can't find 7.0. So you have to turn the page up and go to the next page, and you will find it still have the same heading, but in bracket is continued, and then locate 7.0. And since our 7.0 has no additional digit, then we shall say it is 7.00, and we have to go to the second section of the table, which runs from 0 to 9. And there we select 0. Under the column of 0, we run down until we find where it coincides with the row of 7.0. Where you find the row of 7.0, you take that value, and that will be the logarithm of 7.0. And for this case, we find is 0.8451. So meaning to what we have here, we shall add plus 0.8451. And if we add that one, we are going to have 1.8451. That is how we do find the logarithm of given numbers which are in between the multiples of 10. So with that, that is the logarithm to which 10 must be raised in order to find 70. So in other words, this just simply means that if you take 10 raised to 1.8451, you will get your value as 70. That is what it simply implies. So let's continue on and find how we can find others. Here we have a continuation of the previous session, which was powers of 10 and common logarithms. Now this one is logarithm to base 10, and under here we are going to consider some numbers such as 35.6. And if you have certain number like that, we identify that that number will lie in between 10 and 100, meaning that the logarithm of that number will lie between 1 and 2. That is the logarithm of 10 and logarithm of 100, two bases of 10. Now, to identify what is the specific logarithm of 35.6, the first thing you need to do here is to rewrite that number into standard form. And rewriting in standard form, we shall have 3.56 times 10 raised to power 1. Now we need to find the logarithm of this number to base 10. And if that is the case, it means we shall find the logarithm of 3.56 times 10 raised to power 1 to base 10. But remember here, the reason why we are writing this number into a standard form is to find this decimal part of the logarithm. So the decimal part of the logarithm shall be found by the whole number being written in decimal point here. And then what we have here will give us the whole number of the logarithm part. So that whole number we shall refer it to characteristic part. So let's see how we shall find. Since we have that, remember we said in logarithm, if you have this, it's like adding. If you have multiplication, you will add according to the law of indices, the first law. And here in logarithm, the same will apply. Such that if you have... Now we need to find the value of here. And in this case, we shall have... First, we need to find the logarithm of 10. Then if we have a multiplication, it shall be addition. And then the decimal part of the logarithm here shall be found using the logarithm table. And that is what we shall add to what we shall have found here. And here, the logarithm of 10 raised to 1 is 1. And the logarithm of 3.56, using the mathematical table, you will have to go to the logarithm table. As initially I have shown you how to find. Locate 3.5 under the column of x. After locating 3.5, go on the second section of the table where it runs from 0 to 9. Locate 6 and you will find 6. After getting 6, use that column of 6 to run down until where it will coincide with the row of 3.5, and you will find your value there is 5514. And that 5514, before it at 3.5 initially there at 0 we have a point, so meaning that value is 0.5514. So the value which we have here will be 0. So on this one we are going to add 0.5541. Now we shall add and we shall find the value of, or the logarithm of 35.6 will be equal to 1.5541. That is what we found when we used 3.5, the row of 3.5 and the column of 6. So that's what we find if we work out logarithm of 35.6 to the base of 10 with the help of mathematical table. The same applies to any kind of logarithm that lies between the multiples of 10. You first change the number into a standard form, then you use the mathematical table to help you find the decimal part of the logarithm. Here, as we can see, this is the logarithm of this number. The whole part which is behind the logarithm, behind the decimal point here, is what we refer to characteristic part of the logarithm. And the decimal part here is what we shall refer to as mantissa. It's known as mantissa, and this is the characteristic part. So the whole part, or the whole number part of the logarithm here is the characteristic part, and the decimal part is what we refer to as mantissa. We shall be working out later with some of the examples as we continue on. Next we are going to see how we can find logarithm of positive numbers less than 1. But before that, I will give you an exercise to work out, and that is you will find the logarithm of 792.4. In case you have been given a decimal number or a number which is less than 1, meaning that it is having a decimal, then you are being asked to find the logarithm of that number, which is a positive number, to the base of 10. This is how you should work it out. We shall consider an example on that, and for example, I shall take 0.0003251. In case we have that number and you are being asked to find the logarithm of that number to base of 10, what you are required to do, the first thing is change the number to standard form. And how do you do that? Remember, standard form, we said it takes the kind of m multiplied by 10 raised to n. And if that is the case, then changing that number to that form, we shall rewrite it in form of 3.251 times 10 raised to the power of which the decimal points are moving to the right, and that will be equal to 4. So since you have moved to the right, then it means what you have here will be 10 raised to negative 4. So that is what we have. And in case you want to find the logarithm of that number to the base of 10, then this is what happens. First, find the logarithm of 10 raised to negative 4. You will find is the indices what you will find. That index is negative 4. So you will have negative 4 as the characteristic part. Then you have to find the decimal part, or what we refer to the mantissa part. And the mantissa part here, you will find it by the help of the table, since the logarithm of 3.251 lies between 0 and 1. And finding the logarithm of 3.251, you need a mathematical table to help you find it. And in that case, you shall use the logarithm of number base 10 table, and under the column of x, locate 3.2. After locating 3.2, move to the second section of the table, which runs from 0 to 9, locate 5. Use that column and the row of 3.2 and find where the 2 coincides, and you will find is 0.5119. Then we have an additional 1. Move to the third section of the table where it runs from 1 to 9. Locate 1 and you will find it coincides with 3.2 at 1. And the column there, it is add. So whatever you have there, this one is equal to 4 decimal points or 4 decimal places. So meaning the first one we found was 0.5119. And here we have 1. That one is written in this form. Whatever it is in the add column, it is to 4 decimal places. So on addition, we are going to have 0.5120. That is what we shall find as the logarithm of 3.251. So on this mantissa part, we are going to add this one here, which is positive, and on adding, we shall have 0.5120. So this is the mantissa part and this is the characteristic part. Now another point to note, when you are dealing with logarithm which have negative characteristic, it means that only the characteristic part is the one which is negative, not the mantissa. And in that case, the characteristic part is written with a negative sign on top of it. For example, in computing this, we shall write the negative on top of 4 to mean that only the characteristic part is the one which is negative, but the point will remain the same, and then we shall have 1, 2, 0. This means that the logarithm of this number is this, but only the characteristic part is negative and the mantissa part is positive. And this number is read as bar 4.5120. That is how we do find the logarithm of a number which is positive but less than 1 to the base of 10. Next, let's see how we can find much more. Now you work out, I want you, using the same technique, work out 0.034. Work out the logarithm of that one to the base 10 and see what you will find. The logarithm of 0.034 to base 10. Now, under anti-logarithms, this is the reverse of what we have doing. What we have done, we shall go the reverse of it, and that simply means that in case you know the logarithm of a given number, then you can go back and find the real number to which the logarithm was found in order to find what you have. And in doing that, we shall have the help of anti-logarithm table here to help us find the numbers back. So we shall consider a number such as 0.7125, and that is the logarithm to base 10. A certain number was found to base 10 to give us the value of 0.7125, meaning that the log to base 10 of x is equal to 0.7125. What is the number to which that logarithm was found in order to find this number 0.7125? In order to find that, remember, we say since this is the x, to find that we refer to it as anti-logarithm. And rewriting it is written in this form that we shall have to rewrite it in index form. And writing in index form, we shall have 10 raised to 0.7125 is equal to that number which we need. This one here is our anti-logarithm. And if we work out, we shall find the number to which it was found to the base of 10 to find 0.7125. Let's use the anti-logarithm table and see how it will help us. Now we have anti-logarithm table here, and you will find on top of the anti-logarithm table, it has been written anti-logarithms, and in brackets 10 raised to x. 10 raised to x. Under there we have the same, almost similar but not same, similar to what we had in logarithm table, whereby we have column of x, and then another column which runs from 0 to 9, and then the third one having add, and it runs from 1 to 9. So what do you do? The first column of x, it is point. It starts with the point, and it's 0.0001 that way. So meaning it's 0.00 until onwards. So in case of 0.7125, in order to find the anti-logarithm, you shall view 0 or locate 0.71. Locate 0.71, and you will find it on the next page. After locating 0.71, locate 2, and 2 is in the second section of the table, and then using that that column of 2, run down until where you will coincide with the row of 0.71, and you will find is 5.152. 5.152. And then we have a remainder which is 5. So go to the third part of the table where we have add. Locate 5. Using 5 column, or the fifth column, run down until where you will find or coincide with the row of 0.71, and you will find the value there is 6. So that 6 is in 3 decimal places, so you will add to this, and you will find you will have 5.158. So this is the anti-logarithm of 0.7125. In other words, we do say this is the number to which the logarithm to the base of 10 was found in order to get 0.7125. That's how we do evaluate the anti-logarithms of given logarithms. So we are going to find the anti-logarithm of the following logarithm. That was the first example. Second one is where the characteristic part is negative, and then it's 3.125. The characteristic part is the one which is negative. So to find the anti-logarithm here, what you require is first to write it the way we need to identify it much more clearer. So in that case, we shall have 10 raised to negative 4, since that is the characteristic part. And if you take that one, you multiply by 10 raised to 0.3125. That means I'm separating the characteristic part from the mantissa part. And that is how we do work it out. So we shall find that way. So here, this one already you know how you will find the value. And here we need the anti-logarithm table to help us evaluate which number can we find in case we find the anti-logarithm of 0.3125. And if we find that one, we are going to find, using the same procedure, you will find under the column or the row of 0.31, column of 2, you will find is 2.051. 2.051. Then you will have to add whatever you have there is 5, and under 5 is 2, so it's 0.002. And if you add that, students, you will find is 2.053. So that is what we find at this part, or the mantissa part is giving us the anti-logarithm of that is 2.053. So we shall have 2.053 multiplied by 10 raised to negative 4. And remember, this one is the same as rewriting. Since this one is the negative index, you will have 2.053 multiplied by 1 over 10,000. And if that is the case, you know what happens? You will have a value of 0.002. 0.0002053. This is the number to which the logarithm was found to the base of 10 to give us 4.3125. The same applies to the positive numbers, whereby if it could be positive now, this negative sign could be neglected if it is positive, and the same approach applies, and you will find it out. So I will give you one example of the positive, and I need that one you will work it out as an exercise. That is, find the anti-logarithm of 2.4835. Now let's see how we can find applications of logarithm, or where we can apply logarithms, and then we shall do multiplication and division from the laws of indices. There we can really recall what we had learned in laws of indices, and we did say that if you have, for example, a raised to m, so we shall relate it to base 10. It was a raised to m multiplied by a raised to n. We said it is the same as taking a raised to m plus n. But this one we are going to relate it to the base 10 and say that it shall be 10 raised to m multiplied by 10 raised to n, and this one will give us 10 raised to m plus n, as according to the first law of indices, that is the sum of two powers. And remember, the bases are the same, so meaning that if this is the case, the same case applies to the division, and that means we shall have 10 raised to m divided by 10 raised to n, and this should give us 10m minus n. That is what we refer to as the difference of two powers, as the second law of indices. And this one corresponds to the law of a raised to m divided by a raised to n, and we say it should be a into m minus n. Now we are going to see an application of this into multiplication and division. For example, we have a certain example here: 357 times 47.9. 357 times 47.9. Now, if we do apply the law of logarithm here, and bearing in mind the law of indices, so we shall have this kind, and in that case we are going to have this one will give us the first one, which we have as 357. It will give us 3.57 times 10 raised to power 2. And if you write this one in logarithm form to base 10, let's write it in index form to base 10, whereby we are going to find the logarithm of this number. We shall have 2. Now the logarithm of 3.57, with the help of the mathematical table, you will find the logarithm being 5527. So if you add to these two, you will find you are going to have 5527. So 357 can be still rewritten by writing 10 to power of 2.5527. And now we have 47.9. This one we can still rewrite it as 4.79 times 10 raised to power 1. And this one, in index form, we can still write it as, now this one will be 1 point, and now we are going to find the logarithm of that part. And if we find the logarithm of 4.79 with the help of four-figure elementary mathematical table, you will find it is 6803. 6803. So that is what we are going to have. So in the case of having these numbers here, it's the same as taking this number multiplied by the other number. So since we have the same base now, we have created the same base. So we can have 10 raised to 2.5527 multiplied by 10 raised to 1.6803 is equal to Now, since it is the same base and it's a multiplication sign, then this one will be equal to 2.5527 plus 1.6803. And if we work out, what do you get? You are going to find your value as, this one here will give us, now you will have 4.2330. That is what you find as the value of, if you multiply this directly using the law of indices, and that is the first law. So this is the answer there. But if you go back, what do you find? You will find that this one here is the logarithm of the value which you will find if you multiply this one directly. And if that is the logarithm, we can still find the anti-logarithm of this logarithm and find that number to which you will find the logarithm to the base of 10 and find 4.2330. And if that is the case, this is how we do write the anti-logarithm. So we are finding the anti-logarithm of 4.2330, and that one is the same as writing 10 raised to 4 multiplied by 10 raised to 0.2330. And this one will give us, this one here first is 10 raised to 4. And now we are going to multiply by, now the anti-logarithm of 0.2330, you will find it as, let's use the logarithm table to find it out. And if you find it out, you will have it as 1.71. That's what we are going to find it out. And if you multiply here, you are going to have 17,100. That is what you will find. That is when you use the mathematical table or the logarithm to compute the value of 357 times 47.9. So if you compute this mathematics just directly by long division, you are going to have a value which is equivalent to 17,100.3. So you will find that this 0.3 here is minimal, so we can neglect that one, since what we have is 17,100, which is much more close to this, and this one is just with a minimal range of exceeding. So we can neglect and use this way of computing it. So that is how we can incorporate the application of logarithm in computing mathematics. So we can continue on with the computation and see how we can find out much more of it. Let's deal with now division. We have 864 divided by 136. Again, according to the law of indices, that is the second law, we can still make this one to the base of 10, but firstly we shall work out individually by taking, like this 864, we can rewrite it into 8.64 times 10 raised to power 2. And if that's the case, this number can still be written in form of 10 raised to power 2 point. Now the logarithm of 8.64, you find the logarithm of that number, so that if you find the anti-logarithm of the number which you will have found, you will still get the same value as 864. So we are going to find the logarithm of 8.64, and the logarithm of 8.64 is 9365. 9365. And then again we are going to find the standard form of 136, and the standard form will be 1.36 times 10 raised to power 2. And if you work it out, you will find that the logarithm now will be 2. Now that's the anti-logarithm. If you write 10 and then the logarithm above, that is the anti-logarithm. But if it's just the number alone, is the logarithm of that one to the base of 10. So this is the anti-logarithm with the base 10 of 1.36. Now the logarithm of 1.36 to give us the mantissa part, you will find that the logarithm will be 0.13, 1335. So meaning here, if we add here, we shall have 2.1335. So that is what we find. Remember, we have made the same base, so we can use the law of indices to work it out. And if we apply that law that says that if we have 10 raised to m divided by 10 raised to n, we shall find 10 raised to m minus n. If that is the case, if we apply, we are going to have this one multiplied by this one, or the first computation multiplied by the second, divided by the second computation, meaning 10 raised to 2.9365 divided by 10 raised to 2.1335 is equal to 2.9365 minus 2.1335. And if you compute that, we shall have 10 raised to 0.803. That's what we find. So if you find the anti-logarithm of that number, you are going to find 6.353, and that is the value of 864 divided by 136. That is how we do work out when you incorporate logarithm into multiplication and division from the laws of indices. So we shall consider an example which just directly work out there, and before that we are going to consider even different kinds of them. I shall be dealing with some of the computation you will find and may encounter, or you may find them difficult in working out, such as you may find 3.14. In case you have a number like 3.142 being squared and you want to compute it using logarithm, what do you do? Like this number here, it can be written as 3.14 multiplied by 3.14. So that number, if you compute it in form of logarithm, then it should be, you will have the number which is 3.14. Now it is square. That is the number. And remember, in working out logarithm, please emphasize much more on your spacing and working out. Plan it to be much more needful, such that it will not confuse you while working it out. So for example here, you start with the number, then you write the standard form, and then after the standard form, here you put the logarithm of that number. For this one we have, now in standard form, the number which is in bracket here will be 3.14 times 10 raised to power 0. But remember, this one here is being squared, so it's just that way. So you have 3.14 times 10 raised to power 0, because we are not multiplying by any kind of or to any such that this 10 raised to power 0 will give us 1, and if you multiply with this, you still get the 1 in bracket. Then you find the logarithm of that one. After finding the logarithm, you will find out that the logarithm will be equal to, if you use the mathematical table, you are going to find the logarithm as 0.4969. So you will find is 0.4. Since here we have 0, so we shall start with that as our characteristic. So it's 0.4969. But remember, here we have 2. So 2 means square. We are going to square this. And since we have found the logarithm and it's to base of 10, meaning we have to find this logarithm to base of 10 and then to base of 10. Whatever we shall find, because it is to base 10 and is the logarithm, the sign here will be our addition. Since if we multiply the numbers, the logarithm, we do add them together. So in adding together is like, after finding, since it's square, meaning we should multiply itself twice. So the logarithm we find, we just add another one, of which is the same as taking this one multiplied by 2. And if you do that, you are going to find here, you are going to have a value such as 0.93938 if you go on multiplying. And if you do that, that is what you will find as the logarithm of 3.14 squared. And if that is the logarithm there, and then you can go back and find the anti-logarithm of this number such that you will find the number which is here. So after finding this, you can still find a number x such that if you multiply by 10, or let's just say this is 10 raised to 0, but that number x is in this form, 10 raised to 0.9938. This number, if you do it out, the logarithm of this number, you will find this. So we need that number. So we are going to use anti-logarithm to find the number, and you will find the number is 9.858. So it's to the power 10 raised to 0, so that is what you will have. So if you find the logarithm of this number, you are going to find this. But the anti-logarithm of that, you will find this. And if you compute it out directly by long division, you will find you are having the same answer. My point was this: in case you have a number being squared, it's just the same as finding the logarithm of that number. After finding the logarithm, then you multiply by the power to which it is being squared. If it is 2, multiply by 2. If it is 3, multiply by 3. If it is the fourth, you have to raise to power 4. After finding the logarithm, multiply it by 4. Then you find the anti-logarithm, you will find the same value. So that is how we compute, or we apply logarithm in computing of the squares, cubes, or even the fourth roots of 4 raised to 4, to powers of 4, 5, and so on. Now we are going to see how we can find out or work it in a mathematical mixed computation. For example, we're going to have 634 multiplied by 436 by 688 divided by 784, and see what we shall find. Now you are being told to compute this using logarithm, and if that is the case, what you are required to do here is now what I told you about planning. Planning your work, rearranging it much more well and neatful so that you avoid confusion. And that includes, you write the number here, then the standard form of the number, then you find the logarithm of that number and the computation of that column. So that is how we do separate the numbers in that category. So such that, like for the first number here is 634, I write my 634 here, or 634. In standard form, it will be 6.34 times 10 raised to power 2. If I find the logarithm of that number, I will find is 2 point, now the logarithm of 6.34, I will find is 0.8021. Then I will continue with this one, 436. So right here 436, and that is 4.36 multiplied by 10 raised to power 2. And the logarithm of that number is 2 point, now the logarithm of 4.36, you will find the logarithm of 4.36 is 0.6395. So since we have multiplication here, if we find the logarithm, we are going to add. So I will add here. And if I add, I'm going to get here 6, here 11, 4, 14. So after getting 14, now will be 1.4. So if that's the case, then I'll put here a point, and the one I have to carry I will take it to the characteristic part and I add here 1. So it will be 3 plus 2, I will get 5. I will continue with my calculation down there. So I'm going to multiply by again 688. Now this 688 in standard form is 6.88 times 10 raised to power 2. And this one I will now have to write it down here. So it will be 2. Starting with that, because that is the logarithm of 10 squared. And then the logarithm of 6.8 is equal to 6.88. You will find 6.88 is 0.8376. Now, after getting that, you go step by step. Since we have a multiplication here, it means the logarithm I found here, I'm going to add to the one I will find after computing the logarithm of 688. So I'm going to add. If I add here, I'm going to get 12. This is 8, so I'll find it as 9. And then here will give me 7, here 12. So the one I have currently, I will add it to the characteristic part there. And I will end up having 8.2792. My computation has not ended. So what I'm remaining with, because it's not ended, I'm having the division, and the division is a whole division of 8. So what I will have, I have 784. After computing, I have 784. So in standard form, I'm going to have 7.84 times 10 raised to power 2. And this one will give me 7.84, 7.84 is 0.8943. And since we have a division line here, meaning a quotient rule, then under the laws of indices, we said if it's a quotient rule to the base 10, since we are working to the base of 10, we mean we shall subtract the powers. And this is the same as the power to which 10 must be raised to find 784. And if that's the case, we are going to subtract. And on subtraction, we shall borrow 1. So you will have 12 minus 3, you are going to get 17. Subtract 9, you will have 8. And here we have 11, subtract. Now here you can see, after subtracting here, you borrowed 1 here, you find is 17. You subtract 9, you find 8. Here you are remaining with 1. This one, you can subtract 8 from it. So what you do, you go to characteristic part, and then you borrow 1. After borrowing 1, you bring here will be 11. After getting 11, you subtract 8, you will remain with 3. But remember here you borrowed 1. So if you borrow 1, it remains 7. So 7 minus 2, you will end up having 5. After getting that, that's the value what you find after working out this computation in logarithmic form. So after that, you can go back and find the value to which will give you that figure you have. So what you do, you will come back and write, this is times 10 raised to power 5. The characteristic part, I will write it here. And then the mantissa part, it will be raised to the first 10. So that is 10, and this is 0.3849. Quote me. The characteristic part, you will raise it to the 10 of the last end as we have been doing. Then the decimal part or the mantissa part is which you will raise to the first 10. And then you find the anti-log of this value. And the anti-log, you use the anti-log table. That is 0.38, 0.38, 0.384, and then 9. You'll find it's 2.421. So I can write 2.421. Then you have to add 5. So that is 0.005. And if that is the case, you're going to have 6. So this is what we are going to find. Here is the anti-log. So I'm going to have 2.426 times, now 10 raised to 5, that is 100,000. And if it's the 100,000, if you multiply by that, you are going to have your value as, you will have your answer as 242,600. That is what you find if you compute this numerical problem here using logarithmic form until you find the antilog of the answer and you will arrive at this. That is how we work it out. May it be in bar form. For example, the bar one, if we are told, for example, you may encounter in such a way that after working it out, the multiplication there, you find that this answer here is less than what you have to subtract, or the division part. For example, let's say this one was to be 2.8943. I'm saying this is an example. And here you had, for example, 8 point, for example, let's say 1722. If that was the case, then you can view that the characteristic part there is the denominator having much more than the numerator. So what do? You just subtract the mantissa as normal. So the mantissa will give you, for example, here will be 1, and here you will get 1, here is 2. 9 minus 7 you will have 2. 8 minus 1 is 7. But now for the characteristic part, since after multiplication you have found this one, and it's much more lesser what you have to subtract. Here is a subtraction sign. So what you do, you will just take 2, but you subtract 8. If you take 2 subtract 8, whatever you will find is negative 6. Negative 6. But remember that negative only indicates that the characteristic part is the only one which is negative. So what you do, you put there a bar sign on top of 6 to indicate that only the characteristic part is the one which is negative. And on computing the antilog, then here you should raise to negative 6. But here we remain now the positive part, which is 0.7221. That is how we compute in case you find the one or the quotient is more than the one which you have to subtract. So that's how you compute. Then sometimes there are situations which arise, and you will find, for example, you have to add 2.49, for example, bar 2.49 plus in your computation, and you find you are adding to 3.53. In case you encounter such mathematics, what you do, you will just add it directly, which is bar 2.49 plus, now that one will be here, is bar 3.53. But what I suggest is you separate the characteristic part from the mantissa part, such that you will now have bar 2, then plus 0.49 plus bar 3 plus 0.53, then you add together, and on addition you will find here you will have bar 5 plus 1 point. Now this one is gonna give you 0.2. So if you have something of that sort, as you can see now here, the characteristic part after getting this is positive. So on additional to this, you will now end up having bar 4.02. That is how we compute those having the bar or where the characteristic is negative. You should not confuse between the characteristic and mantissa of logarithm after working it out. Now let's learn more about roots. And under roots we shall be finding either square root, cube root, or any other given or stated roots of certain given numerical figures. For example, you may be given a number like, you have a mathematical problem like 22 multiplied by 56 divided by 63, but here now we have to find the fourth root of this given sum here. For that given condition here, what you are required to do, you shall involve indices and logarithm in working out, and whatever you shall find out, you have to find the fourth root of that given numerical figure. For example, working out this given sum here, if you have been given, may it be multiplied, numerator may be considered even having 4 kinds of given decimals. Maybe you may have a sign of multiplication, division, another one may be even subtraction or given addition here. Whatever you should do, just follow the body mass. Then from there, work out the numerator first, then the denominator, but considering the logarithms law together with the indices law. So after there, and then you find the fourth root of given that value you have found. We shall consider this example and work out and see what we shall find. For example, if you have been given this kind of given mathematical problem, what you are required to do here, if you involve indices and logarithm, then what you are involved to do, you have to construct a table whereby you will have a number, you will have the standard form of that given number, and you will have the logarithm of that number, such that you are going to have a table of that kind. And remember, we have said, in case you have this mathematical problem, you have to deal with the numerator first, then the denominator. For this case, we shall start with number 22, for which we have here. We write it first in standard form. And remember, in writing in standard form, we shall be involving indices kind, such that we shall have 2.2 multiplied by 10 raised to power 1. Since 22, if you write in standard form, you will get that one. And remember, for this case here, this one here, which we have 10 raised to power 1, will form the characteristic part of our logarithm, whereby we shall have 1, then this remaining part here, if we have to find the logarithm of that part, we have to find it, and it will give us the mantissa part of our number there. So we shall use the log table to find the mantissa part, where we shall find it from 2.2. And we shall use the logarithm of numbers, base 10, to find the number 2.2. And you will find 2.2 under column of 0, you will find it's 0.3424. So we shall add 3424. So that is what we have there. And then we shall go for another number, which is 56. The same applies. We shall have 5.6 times 10 raised to power 1. And here we shall have 1 point. Then the mantissa part will be the logarithm to base 10 of 5.6. And we shall find for 5.6, 0.7482. Then remember, we said we have to work with the numerator first. And for this case, the numerator, we are going to take 22 multiplied by 56, meaning that its logarithm shall be, since its multiplication sign, then we shall have an addition sign in the evaluation of its logarithm. For that case, we shall have here 6, here is 10, here we are going to have 9, here is 10, and that one we shall add characteristic part such that we shall have this point as 3.0906. Then we are going to work out the denominator part, and that is 63. So we shall have 6.3 times 10 raised to power 1. And in logarithm form, it will be 1 point, and then we find the characteristic part, the mantissa part of 6.3. The logarithm of 6.3 will give us the mantissa part, and that will be 0.7993. So after having this, since we having that as the denominator, and here we have division sign, then it means for each logarithm we are going to take a subtraction from the numerator. So it will be 6 minus 3, you will remain 3. Here you're going to have 1. Here is 9. And since here we're having now 7. we need to subtract 9. To do that, you have to borrow 1 from the characteristic part. You put here to be 10, you subtract 1, you put here, or you borrow 1 and then you bring here to be 17. Now that 17, you're going to subtract 9. So if you take, it is 18. 18 minus 9, you're going to get 9. Such that here remain 9. 9 subtract 7, you will get your value as 2. And here 2 minus 1, you will have 1. So meaning that whatever you're going to have there, you're going to have 1.2913. So we are going to find this one in this kind, and you will have, this one will be 10 raised to 0.2913 multiplied by 10 raised to power 1. Why? Because the characteristic part will be simply independent, and that will be to base 10, and we will find 10 raised to power 1. And the mantissa part is the one which we need to find the antilog, so as to find the number which will give us that given value. But remember, this value here which we were working for, we cannot work this way because we need to find the fourth root of that given number. For that case, then it means whatever we are having here, we need to find first 1/3 multiplied by a quarter. But if it were that we were not supposed to find this fourth root, then we could just find directly by use of what we have here. But now we need to find the fourth root, and finding the fourth root, we are going to multiply by a quarter, because that is like we are finding the rational index of that given value. So in finding the fourth root, we are going to multiply by a quarter. And remember, if this characteristic part is positive, then we shall just multiply directly. But if this characteristic part was negative, we could make this number in such a way that it is divisible by 4. Let's work with a case where the characteristic part is positive. And if that is the case, we shall just go directly and we shall find this one will give us 0.4225 into 20, and into 30 we shall find 4 into 37, 28, then 5. But this one into just 4 decimal places, we shall have 0.4226. So that is what we are going to have. So we need to find the antilog of that given number. And if we find the antilog of that number, we shall now be finding the value to which resembles that given number. So the antilog, we shall find it as, for 0.242, under the column of 2 is 2.642. 2.642, but we have to add that of the column of 6, and that of the column of 6 is 0.004. So we are going to find the numbers 2.646. So this is the value to which you will find if you find the fourth root of the given value here. Remember what we have done. Work out the numerator first, then the denominator, then you multiply by the root of the fraction of the root which you are finding. That means you divide by the given number or integer, which will be the root sign there. Then from there, you find the antilog to find the given number. Now, what will have happened in case after working the numerator and denominator and you find your value here is negative? The characteristic part is negative. If we were told the characteristic part was negative, in order to work out, for example, if you have 2013, then it means you have to multiply by a quarter, and this means that you will have to make this characteristic part to be divisible by 4 before dividing it by 4. And in such a way, in order to find that, you could take this characteristic part, you add 3, since that is the only least possible number to which we can add to 1 to make it divisible by 4. And remember, if you add 3, this 3 is regarded to be in same condition with bar 1. Since bar 1 means that only this characteristic part is negative, then it implies that even this 3 we are adding can also be negative because we are adding to the characteristic part, such that we shall have bar 4, and it will not be -1 plus 3 such that you get 2. No, it should be in this kind. And remember, whatever you add to the characteristic part should also be applied to mantissa part in such a way that 3.2013, now this one here is what we are going to multiply by a quarter. And in that case now, you shall now get, this one will be bar 4 plus 3.2013 multiplied by a quarter. If you work out, you are going to get, this one here will give you now bar 1 now plus 4 into 3 is 0, so it will be 0.4 into 32 you'll get is 8, and then 4 into 0 is 0 again, and 4 into 1 is 0, so it shall remain that way. 4 into 13 is into 12, you get 3, and so on. So that is what you are going to have. So if you add this, you are going to get bar 1.8003. Now this value here is what you will now required to find the antilog of this, and if you find the antilog is the value which will be corresponding to the respective root you will be asked or required to find. So that is how we do work out in the two perspectives. 1, if the characteristic part is positive, and 2, if the characteristic part is negative. It applies to any given value of root. For example, if it is n, then we could do it with n here. And remember, even if it is bar 1, we have to make it in such a way that it is divisible by n. With that, we have come to the end of our topic today. I believe it has been interesting. See you in our next videos.